Hello, welcome to Electronics Education. I'm Vincent Chang. So it's good to see you in the transistor amplifier analysis for the MOS source follower. MOS source follower. Again, we are going through the lecture starting with analysis by inspection. But before we dive into the source follower, let me show you this. Okay, let's review the small signal model and the relationship between the MOS and the bipolar. Let's start with the bipolar one. On the right-hand side is the model for the bipolar junction transistor. On the left-hand side, you're going to see the MOS. So here's the bipolar high prepaid model. The R pi, V pi. And voltage control current source. Emitter base collector. EB, CE in a common emitter configuration. BE, CE. And there's the T model. Emitter base collector, RE, IE, alpha IE. Current control current source. Voltage control current source. High prepaid model on the top, T model on the bottom. Bipolar. What about the MOS? For the MOS, high prepaid model, voltage control current source. T equivalent, source gate drain. The resistance between source and the gate looking into source is 1 over Gm. Current control current source. And then what's the relationship between the R pi and the RE? 1 plus beta, right? 1 plus beta. R pi equals RE times 1 plus beta. So the relationship between RE and the GM is this. So what's the relationship? What's the bridge? So how to bridge? How to build a bridge between the bipolar and the MOS? Some students, sometimes they said, I like to solve the MOS. But it's challenging for me to solve the bipolar. But there's a very simple relationship between the two. If you just forget about the physical operation, the operation mechanism divides physics. In terms of the relationship between the current, IC equals beta IB, IC equals alpha IE. So in the MOS, the gate current is 0. So it's synonymous to the case when the BJT, the current gain goes to infinity. Or synonymous to the case when the BJT's alpha equals 1. So when beta approach to infinity, then what's the value of R pi? Look at the equation on the top. What's the R pi? Becomes the infinite, right? Right? So what is R pi? R pi is the relationship, is the resistance between gate and the source. Sorry. R pi is the resistance between base and the emitter looking to base. So when R pi approach to infinite, then the resistance between gate and the source looking to gate is equals what? Infinite. Right? Infinity. And then when beta equals infinity, then alpha equals 1. So when alpha equals 1, look at the right hand side equation. RE becomes 1 over Gm. It's exactly what it says on the left. When R pi equals infinity, it's exactly equal to the description between the resistance between the gate and the source looking to gate. In other words, all I want to say is just one word. If you stand on the MOS, because we have studied the bipolar amplifier a lot. We'll study a lot. But that's the foundation. For the MOS is simply a special case. An application, a special case. What special case? So MOS is just a special case of bipolar junction transistor. In the condition of beta equals 1, beta equals infinity, and alpha equals 1. Let me repeat that. MOS is actually a special case of bipolar junction transistor when it means the bipolar junction transistor BJT's current gain, common emitter current gain equals infinity, or common base current gain alpha equals 1. It's just a special case of BJT. It's just a special case of BJT. All right? So that's the key concept of what I want to convey throughout this lecture. So, and then let's just go through the special case, source follower. Because we spend a lot of time on the bipolar emitter follower. So I don't want to belabor too many detail around this similar network, similar circuit, source follower. So now, the first one, input resistance, RG. And then gain, divider. Internal, 1 over GM. External, SL. Right? Right? I forgot what. S over ground to ground. RS, RL, and there's the AC ground on the top. RO. RO. So S, L, and O, external. So again, 1 over GM is the internal resistance. And then the purple highlight is the external one, the SLO. You got it? And then here's the final overall voltage gain. It's easy. What about output resistance? Between source and the ground, RS. Between source and the ground on the top, RO. And there's the AC ground at the gate. So the combination of the three. The combination of three. These three. But let me ask you, why the gate is grounded? Why the gate can be grounded? Because when you take out the external signal source, there's no current flowing around the input loop. So gate is grounded. Gate. When you conduct the output resistance calculation, the gate can be treated as ground. So RS, the first ground, 1 over GM, the second, the third is RO. The combination of the three, the parallel combination. I just want to elaborate what I just said. No current, so gate, the AC voltage of the gate is 0 volt. So 1, 2, 3, boom. So I still encourage you as a beginner, when you first learn this circuit, you need to picture the T equivalent model, T models in your mind with an original circuit. So if you're struggling with this, then just try to draw it out. Just try to draw it out. So VI, R, RG, right? R in is the RG. And then source gate drain. Source gate, drain. So source, gate, drain. The resistance between gate and the source, looking at the source, is 1 over Gm and Is. And then current control, current source. Current control, current source. And O, S, and L. RO, RS, and RL. So for the voltage between VO and the VG is the ratio. External on the top and total, the sum of internal and the external on the bottom in a denominator. This is internal, 1 over Gm, external, the purple one. For the output resistance, is the parallel combination of the three. I don't think I need to explain this again, why the gate can be treated as grounded. The major takeaway for this lecture is try to get familiar with the relationship between the small signal model of the BJT and the MOS. On the right is the two small signal model of BJT. High pre-pack model and T model on the bottom. On the left-hand side, it's counterpart of the high pre-pack model and another counterpart of the T model. And again, MOS small signal model, you can have this perspective. It's just a special case. When the BJT's beta equals infinity, or BJT's alpha, common base current gain, equals 1. The counterpart, the MOS, is just a special case. So I hope you learned something from this lecture. I look forward to seeing you in the next one, the MOS common gate amplifier. Thanks for watching.